Hi, this is Nachammal, myself Nachammal. I now talk about ordinary differential equations. So, now we see about the introduction. In this introduction, we see in the ordinary differential equation what is the order, linearity conditions, initial conditions, and the solutions. Now, I move on to the introduction. In this introduction, we see the derivatives. We know about in the differential equations there are two types of derivatives, that is ordinary derivatives and partial derivatives. Okay, ordinary derivative means dy by dx. We denote that dy by dx. Here y is a function of independent variable. Okay, so y is a dependent variable, x is a independent variable, y is depend on x. And the second one is partial derivatives. Generally, partial derivative is a function of more than one independent variable. Like that, we denote dou u by dou y. Okay, some examples. Ordinary differential equation, d squared y by dx squared plus 6 into xy equal to 1. Here involve one or more ordinary derivatives of unknown functions. In the partial differential equations, dou squared u divided by dou y squared minus dou squared u divided by dou x squared equal to 0. Here it involves one or more partial derivatives of unknown functions. Okay, next the definition. Ordinary differential equations. Here the differential equations involve one or more ordinary derivatives of unknown functions with respect to one independent variable. These are some examples: dy divided by dx minus y equal to e power x, and d squared y divided by dx squared minus 5 into dy by dx plus 2y equal to cos x. Okay, that is in the second equation d squared y by dx square minus 5 into dy by dx plus 2y equal to cos x. Here y of x is an unknown function and x is an independent variable. Next, the order of a differential equation. The order of a differential equation is the order of the highest order derivative. For example, dy by dx minus y equal to e power x. This is the first order ordinary differential equation. Okay, because the order is here 1, and the second equation is d squared y by dx squared minus 5 into dy by dx plus 2y equal to cos x. The order of the given equation is 2, that is d squared y by dx squared. Therefore, this is a second order ordinary differential equation. And also the third equation is d squared y divided by dx squared the whole cube minus dy divided by dx plus 2 into y power 4 equal to 1. This is also a second order ordinary differential equation, but the degree of the second order ordinary differential equation is 3, because the highest derivative of this equation is d squared y by dx squared, but the degree is 3. Okay, next we see the solution of the differential equation. Okay, suppose the equation is given means differential equation. How we have to solve and find out the solution means, for example, x of t equal to e power minus t means we find out the solution of the equation. For that, we have to use the equation d by dt of x of t plus x of t equal to 0. The given condition x of t equal to e power minus t satisfies this equation. So, for initially we find out d by dt of x of t. Here x of t is e power minus t. Therefore, d by dt of x of t equal to minus e power minus t, that is x dash of t. Now, we substitute x of t equal to e power minus t and d by dt of x of t equal to minus e power minus t. Therefore, these two are get cancelled. Therefore, the solution we get answer is 0. Therefore, a solution to a differential equation is a function that satisfies the equation. Next, we see the linear ordinary differential equation. An ordinary differential equation is linear means the unknown function and its derivative appear that power is 1. For example, dy by dx minus y equal to e power x. This is a linear differential ordinary differential equation. And the second one is d squared y divided by dx squared minus 5 into dy by dx plus 2 into x squared y equal to cos x. This is a second order ordinary differential equation, but the highest derivative d square y by dx squared have the power 1. Okay, therefore this is also a linear ordinary differential equation. The third equation is d square y by dx squared the whole cube minus dy by dx plus square root of y equal to 1. So in this equation y have the power 1 by 2 and the higher order derivative d squared y by dx squared have the power 3. Therefore this is a non-linear ordinary differential equation. One of the interesting topic is here boundary value problem and initial value problem. The difference between these two are is we given the auxiliary condition with respect to one point means that is the initial value problem. So we given the auxiliary condition with respect to more than one point means that is the boundary value problem. For example, y double dash plus 2 into y dash plus y equal to e power minus 2x. The auxiliary conditions are y of 0 equal to 1, y dash of 0 equal to 2.5. So we given the condition with respect to 0. Therefore this is the initial value problem. And secondly, boundary value problem. Here the same equation y double dash plus 2y dash plus y equal to e power minus 2x, but we given condition is y of 0 equal to 1 and y of 2 equal to 1.5. So we represent the auxiliary condition with respect to 0 and 2. This is a boundary value problem. So the classification is order means first order, second order, nth order ODEs. Linearity means linear, non-linear. Auxiliary means initial value and boundary value problem. Solution also given that analytic solution, numerical methods to find out the unknown function, and finally ODE and the second order ODE with Euler equation. We solve the first order and second order ODE with the Euler equation. So now the first order ordinary differential equation. This is a linear first order ordinary differential equation. For example, we write that y dash plus p of x into y equal to g of x. We have to solve this equation. So we multiplying the integrating factor mu of x with both sides. Therefore the equation becomes mu of x into dy by dx plus mu of x into p of x into y equal to mu of x into g of x. So we have to assume mu of x into p of x equal to mu dash of x. Now we write that the equation mu of x into dy by dx plus mu dash of x into y equal to mu of x into g of x. Now we applying the product rule. This becomes mu of x into y of x the whole dash equal to mu of x into g of x. Now we integrating on both sides. We get mu of x into y of x equal to integral mu of x into g of x dx plus integral constant c1. I need be the value of y of x. Therefore y of x becomes the numerator integral mu of x g of x dx plus c1 divided by mu of x. Now we have to solve mu of x from the equation number 3. Therefore mu of x into p of x equal to mu dash of x. P of x equal to mu dash of x divided by mu of x. So we taking log on both sides. Therefore logarithm of mu of x the whole dash equal to p of x. So log mu of x equal to integrating. After integrating we get log mu of x equal to integral p of x into dx plus integral constant c2. So taking an exponential on both sides, this becomes mu of x equal to e power integral p dx into dx plus c2. So now we again write it as mu of x equal to c3 into e power integral p of x into dx. So we remove the constant c2, c3. From this we get mu of x equal to e power integral p dx into dx. Therefore the solution of the first order ordinary differential equation becomes y of x equal to integral mu of x into g of x into dx plus c divided by e power integral p dx. Now the summary of this process. Initially we write the differential equation and applying the integrating factor and multiplying mu of x with both sides of the equation, integrating and then solve the equation and find the solution y of x. Okay, for example, y dash minus y equal to e power 2x. Here y of x equal to e power minus integral p dx into dx. Okay, here p of x equal to minus 1. Therefore e power minus of minus 1 into dx. So integrating, integral dx becomes x. Therefore e power x into e power minus x e power 2x into dx plus c. So we taking multiplying with e power x we get y of x equal to c into e power x plus e power 2x. The second example, x into y dash plus 2y equal to x squared minus x, and the condition is y of 1 equal to 1 by 2. Now we divide the entire equation with x. We get y dash plus 2 divided by x into y equal to x minus 1. We applying the same formula, y of x equal to e power minus integral p dx into integral e power integral p of x into dx, g of x into dx plus c. Here p value is 2 divided by x. Okay, e power minus 2 by x into dx into integral e power integral 2 by x into dx into g of x is x minus 1 into dx plus c. So finally we get the answer 1 by 4 into x squared minus 1 by 3 into x plus c into x power minus 2. So applying the given condition, that is y of 1 equal to 1 by 2, that is x equal to 1. So y of 1 equal to 1 by 2. Therefore the LHS becomes 1 by 2. In this RHS 1 by 4 into x squared, that is 1 squared again 1 minus 1 by 3 into 1 plus c into 1 power minus 2. So we get c equal to 7 divided by 12. Next, the second order linear differential equation. So in the second order linear differential equation, we have to solve this equation. We find out the roots. The roots have the type real and distinct, real and equal, and complex roots. And non-homogeneous second order linear differential equation means we apply the undetermined coefficient method and Euler's equations. For example, the general equation of the second order linear differential equation is a y double dash plus b into y dash plus c into y equal to g of x. Here a, b, c are constants, constant coefficients. We applying the sum of two new variables y equal to u plus v. So we replacing that the equation a into u double dash plus p into u dash plus c into u plus a into v double dash plus b into v dash plus cv equal to g of x. Okay, the purpose of this equation is we find out the general solution of the linear differential equation. The solution becomes the complementary function plus particular solution. Okay, for example, a y double dash plus b y dash plus c y equal to 0. Here y equal to e power rx means dy by dx equal to r into e power rx, and d square y by dx squared equal to r squared into e power rx. The characteristic equation becomes e power rx into ar square plus br plus c equal to 0. We solve the characteristic equation. We get the roots real and distinct, or real and equal, and complex roots. Okay, the real and distinct means the equation becomes y equal to c1 into e power r1x plus c2 into e power r2x. For example, y double dash minus 5 into y dash plus 6y equal to 0. The characteristic equation or auxiliary equation becomes m squared minus 5m plus 6 equal to 0, or r squared minus 5r plus 6 equal to 0. So factorizing this equation, we get the root r1 equal to 2 and r2 equal to 3. Here we get real and distinct root. Therefore, the solution becomes general solution y equal to c1 into e power 2x plus c2 into e power 3x. Similarly, we solve the next equation a y double dash plus b y dash plus cy equal to 0. Here the characteristic equation becomes a r squared plus br plus c equal to 0. 2ar, we differentiating the equation 2ar plus b equal to 0. Now we substitute v double dash of x equal to 0. Finally we get v equal to cx plus d. Therefore the solution y becomes y equal to b into e power rx plus cx plus d into e power rx, which is equal to c1 into e power rx plus c2 into x into e power rx. Okay, the complex roots becomes y1 equal to e power lambda x into cos mu x plus I sin mu x, or y2 equal to e power lambda x into cos mu x minus I into sin mu x, because the root becomes lambda plus or minus mu I. Okay, we get the two solution. Therefore y of x equal to c1 into e power lambda x into cos mu x plus c2 into e power lambda x into sin mu x. For examples, y double dash 6y dash plus 9y equal to 0. We write the characteristic equation and then solve. We get the roots r equal to r1 equal to r2 equal to minus 3, real and equal. Therefore the solution becomes y equal to c1 plus c2 into x e power minus 3x. Similarly we solve y double dash minus 4y dash plus 5y equal to 0. After that we write the characteristic equation. We get the roots are 2 plus or minus I. The roots are complex, therefore we write it the solution as y equal to e power 2x into c1 cos x plus c2 sin x, because here mu equal to 2, lambda equal to 2 and mu equal to 1. Next to non-homogeneous. The non-homogeneous equation, write it as a y double dash plus b y dash plus c y equal to g of x. Here y equal to k divided by c. It is a particular solution of the given equation, and g of x is a polynomial, means this polynomial of order n, means the form of the particular solution is y equal to alpha naught plus alpha 1x plus alpha 2x square plus etc. alpha n x power n. So the equation is y double dash minus 4y dash plus 4y equal to 4x plus 8x cube. Now we find out the equation y dash and y double dash and y. So we get the characteristic equation of the function is y double dash minus 4y dash plus 4y equal to 0. That is r square minus 4r plus 4 equal to 0. We solve that equation, r equal to 2. The solution becomes y equal to c1 plus c2x into e power 2x. Now we equating the coefficients becomes yp equal to 7 plus 10x plus 6x square plus 2x cube. Therefore the final solution becomes y equal to yc plus yp, that is c1 plus c2x into e power 2x plus 7 plus 10x plus 6x square plus 2x cube. Next, the next type is, suppose g of x is of the form t into e power rx, means here a equal to t divided by ar square plus br plus c, means the solution, particular solution becomes y equal to e into sin nx plus f into cos nx. Here e equal to c minus n square a into c plus n b d divided by c minus n square a the whole square plus n square b square, and f equal to c minus n square a into c minus n b d divided by c minus n square a the whole square plus n square b square. Example, 3y double dash minus 6y dash equal to 18. Here y equal to cs, y dash equal to c, and then again differentiating y double dash equal to 0. Substituting the values in the equation, 3y double dash minus 6y dash equal to 18. We get the value of c equal to minus 3. That is here yp equal to minus 3x. And similarly we write the another side, the characteristic equation of the given equation. It becomes 3r square minus 6r equal to 0. Now factorizing the equation, we get the roots becomes r equal to 0 and r equal to 0. That is the first root is 0, second root is 2. Therefore yc equal to c1 plus c2 into e power 2x. The overall solution y becomes yc plus yp equal to minus 3x plus c1 plus c2 into e power 2x. So some more examples. 3y double dash plus 10y dash minus 8y equal to 7 into e power minus 4x. Now we find out first derivative and second derivative from the equation y equal to c into x into e power minus 4x, and then find the c value minus 1 by 2. The same process we get the characteristic equation and then find the root of the equation. Finally we write the y equal to yc plus yp minus 1 by 2 into x e power minus 4x plus a into e power 2x by 3 plus b into e power minus 4x. The same process we apply the next examples. Finally we see the Euler's equations. Okay, Euler's equation we write it as a into x squared into y double dash plus p into xy dash plus cy equal to 0. Here we assume that x greater than 0 means the solutions of the form y of x equal to x power r. So the equation, differential equation, in this differential equation we write the characteristic equation like that: a r into r minus 1 plus b into b of r plus c equal to 0. There are three cases here we discuss that. Here also the characteristic equation we solve it. There do different the three different types of cases appear. The first case we see that real solution and distinct. On the suppose y equal to x power r1 and y equal to x power r2 means the original equation becomes y of x equal to c1 into x power r1 plus c2 into x power r2. This is a general solution of the original solution. For example, 2 into x square y double dash plus 3 into xy dash minus 15 into y equal to 0. The characteristic equation is 2 into r minus 1 plus 3 into r minus 15 equal to 0. Now we solve the equation. We get r1 equal to 5 divided by 2 and r2 equal to minus 3. Therefore, the solution becomes y of x equal to c1 into x power r1. We substitute r1 is 5 by 2 and c2 into x power r2, substitute r2 equal to minus 3. Therefore, the second case is r1 equal to r2 equal to r, that is the two roots are equal. Therefore, we write it as y of x equal to c1 into x power 4 plus c2 into x power 4 into log x. The solution of the equation is x squared into y double dash minus 7 into xy dash plus 16y equal to 0. So similarly we write the characteristic equation. We get r1 r2 equal to 4. Therefore y of x equal to c1 into x power 4 plus c2 into x power 4 into log x. The final case is solve the characteristic equation. We get the two complex roots, that is CR1, 2 equal to lambda plus or minus mu I. Therefore, we write it as x power lambda plus mu I. Another one x power lambda minus mu I. Therefore, e power lambda plus or minus mu I log of x. X power lambda into cos of mu into log x plus or minus I into x power lambda into sin mu of log x. Therefore, the final solution becomes y of x equal to x power lambda c1 into cos of mu log x plus c2 into sin of mu log x. The example is x squared into y double dash plus 3 into xy dash plus 4 into y equal to 0. We write the characteristic equation is r into r minus 1 plus 3r plus 4 equal to 0. The root becomes minus 1 plus or minus square root of 3i. The solution of the equation is y of x equal to c1 into 1 by x or x power minus 1 into cos of root 3 into log x plus c2 into x power minus 1 into sin root 3 into log x. Thank you.